All right, so in this video, we're going to do a practice problem with Tanabe-Sugano diagrams. In this problem, let's just read it. It says the UV-Vis spectrum of a chromium 3 plus complex has peaks at 8,000, 13,600, and 23,200 wave numbers. What is delta O? So we're given the energies of three transitions. We're given the identity of the complex. We don't know anything about what ligands are involved, but we're asked for delta O, and that's a key thing, right? Because that's telling us that this is actually an octahedral complex, because can't have delta O if it's anything else. So it's not tetrahedral. That would be then delta T. So we know it's octahedral. That's the first part. We know we're going to have to use a Tanabe-Sugano diagram to calculate delta O. And so we first need to figure out how many d electrons we have, so we know which Tanabe-Sugano diagram to use. We're a chromium 3 plus. Chromium is in group 6. So chromium has 6 electrons, but we're a 3 plus oxidation state. So we subtract off, remove 3 of those electrons. So we get 3. So this is a D3 complex that we're talking about. And that means that we're going to have to use the D3 Tanabe-Sugano diagram. And that's what I pulled up here. If this were tetrahedral, chromium 3 plus, we would have to use the D7, the 10 minus 3 tetrahedral diagram. But it's octahedral, so we just use the D3 Tanabe-Sugano diagram. And let's identify the different spin allowed states here so that we can make assignments. Our ground state is going to be a quartet A2G. And then we have three excited states. We have a quartet T2G, matting G's because we're an octahedral. An octahedral, you have an inversion center. So you have Garada, which means symmetric to the inversion center in the Mulliken symbols. And we have a quartet T1G, and we have a quartet T1G, another quartet T1G. These are going to be our three spin allowed transitions going from the ground state to the excited states. Spin allowed because we went from quartet to quartet. We can't change the spin when we're talking about spin allowed states. So I'm just going to write these out here. Our first transition is quartet A2G to quartet T2G. And we know the energy of that transition, call it E1, is 8,000 wave numbers. Our next one is, again, going to that same ground state circled in black, adding a G because we're octahedral, quartet A2G, going to quartet T1G, and E2 is 13,600 wave numbers. And our last one is quartet A2G going to a different quartet T1G, different names. Those are same names, but different states. They just have the same symmetry, but they're different states. They have different energies. And that's our E3. So those are our assignments. It's very nice that in this practice problem, they gave us 3 peaks and we only have 3 spin allowed transitions. So it kind of gives us some confidence that we picked the right Tanabe-Sugano diagram. But, you know, in some cases, they might give you only 2 peaks, but there's still, let's say, 3 spin allowed transitions. And the UV-Vis spectrum might have only shown 2 peaks because the third peak was so high in energy, it was off the charts of the range of where the UV-Vis spectrometer could access. It's too far in the ultraviolet, too high in energy. So just keep that in mind. You know, you just don't necessarily need, depending on how the problems are manufactured, you don't necessarily need to have this matching where we had 3 spin allowed states here and they gave me 3 peaks. Great, but in this case it works out. Now if somehow they gave me 4 peaks, 4 main peaks, and I knew they're all D to D transitions from some other information, then I would be in trouble here because I only have 3 spin allowed. You know, if I knew there were 4 DD spin allowed transitions. But anyway, so the crux of this problem is figuring out where we are on this Tanabe-Sugano diagram. Where are we in terms of the x-axis? We don't know what the ligands are. Once we figure out where we are on the x-axis, we'll be able to solve for delta O, right? Delta is given here. So that's where we have to figure out. And so the way to do this is to look at the ratios of the peaks. And so we're going to take the ratio of E3 to E1. That's going to be 23,200 wave numbers over 8,000 wave numbers. You plug that into your calculator and you get 2.9. And then we're going to do the same thing for E3 and E2. You can also do E2 to E1. Doesn't really matter. But in this case, I'll do it this way. And 23,200 divided by 13,600 gets you 1.7 when you plug it into your calculator. So what you're doing here now is you're going to be sliding along, testing different values on the x-axis, and figuring out when do I hit these ratios, or at least hit these ratios close enough to call it good enough. So that's what we're going to do. And the way I'm going to do this is I'm just going to say, I'm going to do some tests. So I'm going to test if E1 over B, right? This is in units of E over B. So if E1, our first transition divided by B, equals 30, what would my ratios be? E3 over 1, what would that equal? And E3 over E2. And so at a 30 E1 over B, I'm at this y-axis point for my first transition. And I'm going to highlight this in red here just so we can see this line more clearly. And I'm going to do the same thing in green. I like to do this, especially on the Tanabe-Sugano diagrams that have high spin and low spin. They can get quite messy. So it's nice to highlight them somehow. Okay. So if I'm at 30 over B for my value, where does that mean for E1? That means I'm going to be right about here-ish, right? I'm just, use a ruler, go over, and then where do I intersect at my red line, which is the energy of my first transition, right? Okay. So then what we're doing is we are looking at what our energy is going to be for E3 over E1. So we need to figure out now if I'm at this position, right around 3.1 delta over B, ligands with that strength, I'm going to get 30 for my E1 over B. So what is my value of my E3? And so I just got to go up from the straight line from here. And you can see I'm about, 60, call it 62. So I'm, so my E3 over B is 62. So just to show you how this works, to be, rigorous, my E3 over B equals 62, and my E1 over B is 30, that's how I defined. So it would be E3 over B divided by, so I flip this, E1, my B's cancel, that's going to get me 62 over 30, which is 2 point something. Let me plug it in here. $62 over 30, 2.1. Okay. So that gets you E3 over E1, right? Which is what we just solved for. So you can see how the B's cancel. I'm not going to do that every single time because we're going to be testing a lot here. I just wanted to walk you through how the B's cancel there. But that's, technically what is happening. All you have to do is divide the value you see, right, on the y-axis by your other y-axis value, which we set to be equal to 30. We're testing the 30 value. So we're just dividing that. Okay, so 2.1. What about our E3 to E2? So now we go down. So E3 we said was 62, and we go down here, and it looks like we're right around maybe 39. So we're going to get 62 divided by 39. That is 1.6. What was 62 divided by 39? Those were my estimations. You'll have to use a ruler on this to get, more accurate. So those aren't matching super well. This one's okay, 1.7, 1.6, but 2.9, 2.1, we can probably do better. So let's look. Let's try E1 over B. If E1 over B equals 20. So we're going to test a different value here. And again, we're asking what our E3 over E1 is and what our E3 over E2 is. And we're trying to get something close to 2.9 and 1.7 to match these values and have the right ratios. So if we're at 20, or E1 over B, well, this is E over B, so we're at 20. So we have to figure out where that first transition equals 20. So right around here, right where delta over B equals 2. And so then we go straight up to here, and that's our E3. And I don't know, we're at 43 maybe, call it. So that's going to be 43 divided by 20. That's going to be our ratio. That ends up being 2.2. So we got a little closer. At least we're going in the right direction. We're going up, marching up to 2.9, but we're still not quite there. And we could do the same thing for E3 versus E2. We're going up here to the green line, and it looks like we're at maybe 28, 29. Again, without a ruler, this isn't super precise. But if I say I'm at 28, I get a value of 1.5. All right, and so let's test another point. Let's keep marching to the left. If E1 over B equals 10, what is my E3 over E1 ratio? And what is my E3 over E2 ratio? If we're at 10, we're going to be right around there. That's where we intersect with the 1. And we go up, and I'm going to, maybe a little bit over, right around there. So we're pretty close to 29. Now, if we get a value of 29, of course, we're going to get 2.9, which is what we're shooting for, but it's close. Right? Maybe it's 11, maybe it's 9 here where we're supposed to be, but it's close. We got a value of 2.9, right? Because we had 29 here, and we had 10 here is what we tested, the point we tested. And then we'll test the E2 point, and so that going up is going to be about, looks like maybe 17 or 16. So if we do 29 divided by 17, we got 1.7, which actually turns out to be perfect. So we found a match. You won't necessarily get perfect. And again, whether or not you're at right here or here on the graph, it's going to be hard to tell most of the times on these diagrams. But we know that this is a good estimate. E1 over B is going to be equal to 10. Okay, so if we know that, now we can solve for B. And so we know our transitions we're right around this area. So our first transition is there. Our second transition that's worth what? 13,600 wave numbers is there, going from ground state to excited state. And our third transition is here. That's where we are. We did the hardest part of the problem. Now we just have to do some math to figure out what B is and what delta O is. We know E1 is 8,000 wave numbers as given to us in a way. And so 8,000 divided by B equals 10, because now we know that this value that we tested was about right. So then we just go, solve for this. 8,000 divided by 10 is going to be equal to 800 wave numbers. So our Rockoff parameter is equal to 800 wave numbers. Okay, and then we know we're right around delta B equals 1. So delta over B. equals 1. And so our V value here is also going to just be equal to B, which is 800 wave numbers. So delta O, we can call it, because we're an octahedral, is equal to 800 wave numbers. So there is something to be careful about here, and it's what type of Tanabe-Sugano diagram you're pulling up and what the units are down here. And actually, what we did here is going to be wrong in terms of our delta O. Our delta O is actually 10 times higher than this. It's going to be 8,000. And it's because this Tanabe-Sugano diagram that we pulled up is actually in units of dq and not delta O. So there's two different units to talk about these things, and delta O is 10 dq. So because this is in units of dq, unfortunately, this delta here, you have to multiply by 10. I'd probably suggest using other Tanabe-Sugano diagrams. If you look at it, these values here will actually be 10, 20, and 30. And so your value here is going to end up being 10 instead of 1. And so then you're going to get this 8,000 number instead of 800. But the mechanics of all this are the same. Unfortunately, there's just multiple units that are used here, and so I apologize for that, but it's just sort of the way it is.